So without further ado, join me in welcoming Jasper.
Thank you. So maybe we should start easy, because this is quite a complex talk. Who here knows what it feels like to be about 30 feet away from a type 1 supernova? I actually can't see how many hands are being raised right now, because I am. Anyway, yeah, I'm pretty excited to be here. I'm going to be talking about applying deep learning to side channel problems. And I'm particularly interested in this topic because I've been doing security professionally since about 2001 and machine learning as a hobby since about 1999. So this was even before all the deep learning stuff. But even beyond that, I think more importantly, what we're facing right now in the world is just huge amount of security issues. And really the only way that we're going to overcome this is to scale up our testing capabilities, our problem-solving capabilities. And I think machine learning is one way of doing that, so I'm pretty excited to show that to you. Also, this work wouldn't have been possible without my two colleagues, Guilherme and Baris as well, who hopefully are fast asleep right now in a different continent. So let's get started. Oh wait, I have a clicker thing. It's on. It's not on. And it's working. So before, when we were doing side channel analysis, the main steps are we take a chip, we measure its power consumption, we do some fancy signal processing, we do some leakage modeling, and then out comes the cryptographic key, if we're successful. If you look at academic literature, they've studied a lot this leakage modeling and the key retrieval part, which is kind of the science in side channel analysis. But there's also really an art and kind of human skill involved in getting your signals acquired in the right way and transforming them in such a way that you actually can do the leakage modeling and the key extraction. So this is an obvious bottleneck in scaling up these kind of tests. So what we've been researching is what happens if we replace those two yellow boxes there with a neural network, specifically a deep neural network. So that's what I'm going to be talking about. And for that, normally I would now take a survey of like who knows DPA and who knows deep learning, but I can't see you anyway. So I'll just dive into the basics of both, and then I'll explain the experiments that we did and the results that we got. So let's first do power and EM side channel analysis. And for the sake of time, I'm going to stay pretty abstract, which also means that I'm not 100% correct, but you can ask me questions later. So the first stage of side channel analysis is very sexy. Obviously, we have oscilloscopes, we have devices, we acquire all these cool traces. And this is still a manual part, even with what we're doing with deep learning now. We don't have our robots trained yet to connect these little boards. But after this stage, we're going to do something else. But traditionally, you would start there and you get these kind of traces. So this is a power profile from some crypto algorithm that's executing. Bonus points if you come after the talk to me and tell me what it is. And the whole goal is just to extract this cryptographic key from the power consumption. Now, this is just step one. After you've taken these traces, I'll actually show you kind of what you can see. This is one example of a trace. And this one actually has huge leakage. You can't see that yet because you have to zoom in a little bit. So if you zoom in, here you see the execution of almost 2 full clock cycles of a device. And if you take a number of these traces and then overlap them, you can start seeing where the traces start to diverge. And that can actually mean two things. It can be really huge data leakage, or it can be some noise. Now, I'm saying really huge data leakage because here you can visually see that the traces are actually diverging, which normally, if you have a fairly well-protected device, the leakage is below the noise threshold. So you're not going to be able to see it with the naked eye. You need some kind of statistics and filtering to get to that point. So let me just take one sip of water and then just dive right in. I prefer to show things live. There's always a bit of risk associated, obviously, but let's do it anyway. Oh, what a beautiful trace. Don't worry, I also see just a blue band here. There's nothing to see here. It's not until you start zooming in that there's some stuff happening. This is actually quite ugly. I can blow it up a bit further if you're interested. I don't see a whole lot of pattern here. It's big blocks, etc. So here comes that first phase of I need to do something with this signal to make it pretty. So with this one, I happen to know what buttons to press, so let's just do that. So I'm actually taking an absolute value in a low pass, which kind of calculates an envelope over the signal. So I get again this trace, nice and blue, and then do a low pass filter. Now it's starting to look like something. Right? So if I zoom in now, you can start seeing a nice, like, repetitive pattern there. This is actually an ECC implementation if you're interested. But normally this takes a little bit of fiddling with the signal, right? I've now done the happy flow, but normally you don't know what to do in this filtering process. So there's a similar problem you need to overcome. I'll show you directly here. Which one was I going to do? I was going to do this one. No, wrong one. This one, another beautiful signal. What you see if I scroll through the signals here, you can kind of see it's jumping back and forth. So we call this misalignment. So the traces aren't really like properly aligned, which is a problem for the algorithms further down the road. So obviously we have solutions to this. So we take an area like this here and we perform an alignment of it. Ignore for now what I'm typing in. And crunch, crunch, crunch. I pressed the wrong here. I'm only going to do it on 100 traces, otherwise it takes too long. And the problem is I'm not really getting any results. And this is not a problem of the demo, but it's the problem that I put in the wrong parameters. And this is the problem with humans. You have to try a lot of things and sometimes you screw things up. I can actually make this one work if I, just so you see that I'm not kidding. If I take this signal, I do an alignment, I only take 100 traces. And instead of the matching threshold is basically what the correlation needs to be for it to say, okay, this is a nice overlap. I put that a little bit lower, so I fiddle with the parameters, and now I get 100 traces, actually 84 traces, so I dropped a few that are supposedly aligned. And if I scroll down, it's not much better, right? It's still jumping a bit. What you do see is that this area that I selected before, I'll zoom in on it a little bit. Now actually, it does seem to overlap. So something has happened, but I'm still not there. So this is still part of kind of the art of doing side channel analysis. You have all these tools, alignment, filtering, etc. But you need experience and knowledge of these tools to figure out how to put them together before you can really prepare your signal into something useful. So let's move to the science part. So we talked about signal processing, misalignment. So what's really going on here? I just want to give you a gist of what I'm going to do with all these signals. So let's say we have an AES 128 implementation. And if you look at the first part of the first round, it gets a 16-byte input vector. It XORs the key in. The key is what we're interested in. That's what we want to know, but we don't know it. Then out comes some data, which goes through an S-box. And after the S-box, you get some more intermediate data, and there's a whole lot more AES happening after that. But what we're interested in is modeling the power consumption of this device just after it's executed the S-box. The reason for that is that if we, let's say, let's say we take S0 there, that intermediate. If we can predict, maybe not exactly, but maybe probabilistically, what the value for S0 is, that means we can actually work back through the S box and say what X0 is, which means that if we know the input, which is an assumption in DPA, we can calculate what the key byte is. So it's really important to understand that there's this relation between the power consumption of intermediate values and the actual key values. I might not be predicting exactly the key value, but something that allows me to calculate it. Also, this is always probabilistically. So instead of learning exactly what S0 is, we get a probability distribution over all the values for S0, which we can calculate back to a probability distribution over all the values of K0. So it gives us just some statistics on what this key is. And if we do this over and over and over again for multiple traces, those statistics will start to accumulate and I can cancel out noise. And eventually there's this one key byte which sort of has the highest probability. And that's the one we use. Once you have one key byte, you just repeat the whole process for all the other ones and then you get the full AES key. Now another step in doing side channel analysis is what we call point of interest selection, which basically is what we just talked about. So we want to predict what the S-box output is. Ideally, we don't analyze the entire trace, we only analyze the part where this S-box out value is present. This is particularly important for the template attacks, which I'll talk about in the next slide. Because they're very sensitive to putting in samples or parts of a trace that actually have nothing to do with the key. They add so much noise that the number of training traces that you need is too much to actually do some decent key extraction. So when I say template analysis, the basic process is that I want to take a device for which I can program the key, build these templates, or they're basically models that relate these intermediate values to the power usage. And then once I get either the same device but maybe a different app or another device with the same chip, I can apply my learn templates and learn what the actual key is. So on the one hand, I'm building templates from power traces. In the bottom hand, I'm taking these templates and I'm matching them to power traces in order to get keys out again. And again, these are probabilistic methods. So I need a bunch of traces in order for my templates to output the correct key byte with some confidence. After we've done this, we do something which is called the key recovery phase. And what you see on this slide is on the x-axis the number of traces that we're using to attack a device. And on the y-axis you see the rank of the correct key byte. So let's say this is in a test scenario, right? So we know what the actual key is, but now we're going to try to see how close we are to actually extracting that key. So a plot like this shows that. So this ranking comes from the probabilities that you're building up over all the keys. So you can see in the beginning, on average, that rank will be about 128, right? In the middle between 0 and 255. And the more statistics you accumulate, the lower that actual key byte will drop in the ranking. And as soon as all 16 key bytes are at rank 0, we've actually found the key. So that's what happens at the back there. And an often used metric for this is just the number of traces that you need to extract the key. So as soon as you see these plots, all the lines kind of converge to 0. That's the point where you can extract the key. So for this device, we would say we can extract the key in like 5,000 traces. So that's not a very strong device. Now, obviously, I've been just lying to you because this all looks like a waterfall process. You do some filtering, and you do some leakage modeling, and then out comes the key. This is not reality. In reality, you make an acquisition, you do some filtering, the filtering doesn't work, you go back to the drawing board. do some leakage modeling, still the key doesn't come out, you find out you didn't connect the wire during the acquisition, so you go back to that, and this is really an ongoing process that's, in which humans are involved. It's basically using tools and getting feedback and trying to get basically all the stars aligned in order to get a key out. So part of this, and specifically the processing and analysis step, that's what we're going to tackle with deep learning. So let me talk about that for a moment. So just in general, when you're applying or when you're doing deep learning, really what you're interested in is separating dogs from cats, at least when you have classification problems. So we have some labeled images of cats, we have some labeled images of dogs, and we're going to try to build a machine that once you give it a new picture, it will say this is a cat with X% probability and a dog with 1 minus X% probability. So in order to do that, we feed it with all these examples, and we're training the machine, or a network in this case. And in your initial step, your machine is going to be pretty poor at doing this kind of classification. So out come some probabilities that really don't represent what the input is. What you run there is a so-called backpropagation algorithm. And there's a lot of literature on deep learning on how to run this and different variants and everything. But basically you're tweaking the machine to do just a little bit better. And if you keep on doing this over and over and over again, ideally, your machine just gets better and better and better at the classification. So once you have a candidate where you think like this now works quite well in classification, you test the machine on new data that it hasn't seen yet. So this is called validation data. If the accuracy is good enough on this validation data, then good, you're happy. Otherwise, you're going to have to tweak your machine a little bit. And obviously, you're going to be in that no cycle for a couple times before you hit the yes, and I'll show you that as well. So just to peek a little bit under the hood here, we're going to be using one specific type of network, which is called a convolutional neural network. And it was actually designed for image processing, but it has some parallels with side channel analysis that actually made it interesting enough for us to take a look at to see if it applies there as well. What it really does is it has an input layer, which is just a representation of your input. In the case of cat pictures, it's just 1 neuron per pixel, 3 I guess if you're doing color. Then you have a number of convolutional layers. And these convolutional layers, they're trained to extract certain features. So for instance, in the first layer, it might be just extracting edges. In the next layer, it might use this information of edges to construct an eye and a nose, some cute fluffy ears. And then in the next layer, it will combine this to recognize a cat face, for instance. After that is a number of layers, which we call the dense layers. And these are used for classification. So they take this kind of feature extracted and coded information and turn it into a probability for a certain class, cat or dog. And the cool thing about the convolutional part is that it's actually able to detect features independent of their position and also scale. So you can see I can rotate this cat up. Don't do this in real life, it's really cruel to the kitties. But on the pictures you can turn them upside down and left and right, and it will still detect them. And if you remember our misalignment example, that's kind of a similar thing that's happening there. Like there's just traces that are dancing around, they're not exactly in the same place. So we're hoping that these the properties of this convolutional network help us in recovering information anyway. So once we apply this to our type of data, really what we're doing is we're taking these traces and we're turning them into one input vector. Basically one neuron per sample that we have in the trace. And we don't label them as cats and dogs, but we label them by the Hamming weight of, for instance, the output of the S-box. You can ask me later why Hamming weight. And this is called the leakage model that we're using. That's a term from side channel analysis. But basically this is again a classification problem. We take in a trace and we want to figure out what the Hamming weight of that S0 value is. Now once we've trained this, we actually can do the classification. So we again input a trace that it's never seen before. It runs through the deep learning network, and the output, again, just like with the template attack, is a probability distribution over the different Hamming weights. And this allows me to calculate a probability distribution over key values. So it's a very compatible problem. So we pulled this out and plugged it into our side channel engine. Yeah, obviously you can actually use the same key enumeration after this. So that was that in theory. Let's look at the practice for a second. Let's first go and do this. So I'll open up a trace here, blow it up for the people in the back and or with bad eyes. And I wish I had time to go into all these parameters, but I don't. But basically what I'm doing is I'm configuring here the neural network that I want to do to attack this particular trace set. In this case, I'm making a way too small network, so it actually won't be able to learn from this, but let's see. So it's just one dense layer with 10 neurons, and I threw out the convolutional part. So I'll run this. Now normally you would take a farm of GPUs and crunch over it. Now my poor laptop, for some technical reason, doesn't support the GPU in this particular application. But there's one advantage we have, and that's we're actually doing this not on big data. We're doing this on fairly small data. It's almost done its computation. Let me just set this back. And for everybody who cannot read this, what it's saying here is the correct key was hex value 6C, and it found key 8A. In other words, it failed to recover the correct key. So this is what happens, obviously, when you start doing deep learning, because nothing works out of the box, ever. I guess that's more of a live thing than a deep learning thing. So we need to do a little bit more work. So we need to actually think a little bit about the structure of this network. So obviously the network that I just selected with one layer, 10 neurons, it's not working on this particular example. So there's a few things. I can't give you like numbers right now that work because it depends on the trace set that you have and the noise characteristics, leakage characteristics. But basically if you have a trace set, the input neuron size is the length, the number of samples. That one's easy. The number of convolutional steps we find basically depends on how much misalignment you have. If you have almost no misalignment, then you almost don't need that layer. The more you have, the more of these layers you'll need. Similarly, playing with the size of the dense layers also allows you to classify some targets and some not. But I'll give you a general strategy on how to figure out how you get to the right parameters. So the first thing we try to do is make sure that the whole network is actually capable of learning. That's kind of a good base case to check. So what you need to do is you need to make a network that's complex enough to be able to capture all these classes and get a really high, as we call accuracy or recall. And you see that on the left-hand side of this screen. So as the network is training throughout time, the recall goes, or in this case it's accuracy, goes up, which means that I'm learning from my data. I'm getting better and better at representing it. On the right-hand side, you see the loss function, which is another representation of seeing how well your network is. Which is great. Okay, now we have a network that's actually capable of learning. The problem is that if you make a network too complex, it suffers from what's called the memorization effect. So if you make a really complex network, it can actually start memorizing every input you've given it and get a perfect classification. But you give it some other input, which it's never seen before, terrible classification rates. So what do you do next? So I make my network bigger and bigger until I get a good training accuracy. Now I gotta make sure that my validation accuracy goes up. So this is the picture that you want to see. So on the gray you see the train set. It needs to go up and up and up. The network needs to be learning. But you need to see that the validation recall or accuracy also goes up. If you don't have that, then your network is not generalizing. You're actually not learning, you're just memorizing. What you do, if you look for this special threshold here, so in the case of the Hamming weight of a byte, there are actually 9 classes, because you have Hamming weight 0 to 8. Which means that if I flip a coin and I say the Hamming weight of this trace is blah, I'm right 1 out of 9 times. So that's actually the minimum accuracy that you want to see, or recall that you want to see. As soon as it goes above that, that means you're generalizing. So you're actually seeing in your validation set that you're better than coin flip accuracy. There's other techniques for making the network, or there's techniques for making the network generalize. I mentioned a couple of here, but I'll just highlight the data augmentation part. So if you have very few examples, you can actually artificially create new examples. And the way you do that, for instance, let's say I have a trace set that's somewhat misaligned. I can actually take the first trace and generate 10 examples of that with different misalignments. And this will actually help the network understand misalignment better, because it's just getting more traces that are misaligned, and it will learn how to cover for that. There's other techniques like L1, L2 regularization, dropout, early stopping. Deep learning literature will talk about that in detail. And really, in the end, we get again these Hamming weight distributions over key byte values, and we can just run the key recovery as we've done before. Now, I already hinted earlier at the fact that I don't need big data. And the reason is that the classification we're doing here is actually slightly different from cat pictures. And this is an insight that our team only had after starting this. Because in the beginning you're like, hey, we have like 100 gazillion trillion cat pictures that we need to train this hugely deep network, and then it will get good generalization. But what you're trying to achieve there is to classify each individual picture very well. And that's not what we're trying to do here. We're trying to accumulate statistics about one single key byte. And that's different. All we need to do is be just slightly above coin flip accuracy in our classification, and over time our statistics will accumulate and we'll point to the right key anyway. So this is why we also, what you see here, actually I copy pasted this picture, so don't look at this. But I'll show you later in examples that we did. We need ballpark about the same number of traces that we did for other analyses as well. So we don't need big data in this case, which is great. So let's move to the actual meat here. So let's get keys from things. Let me just show you this trace. It's another trace that's, we start obviously with the toy examples. Close this guy. Oops. So here you can see a nicely misaligned trace. Actually, what I do when I'm looking at this kind of stuff, especially when it gets later at night, you just run some techno music and you pretend that you're a VJ. Kidding aside, so this obviously is a trace that you need to realign first before you do the analysis, but we're not going to do that. We're just going to see what happens when we run deep learning on this. And just for your information, this is coming off a Cortex M4 CPU running at 168 megahertz or so. So it's not super fast, but it works for this example. So what we do is we build a neural network using the trial and error and the process that I've shown you before. And we end up with something with, in this case, 3 convolutional layers, 3 dense layers, an output layer. And what we have in this set is 90,000 training traces, which takes you, I don't know, half hour to acquire or so. Then we use 5,000 traces for validation and 5,000 for the test. And we're using the Hamming weight of the S-box out. Also in this case, we use the data augmentation that I just talked about to train the network to also recognize misalignment. What we're seeing is the pictures that we like to see. So the recall goes up for both the training and validation set. The loss function goes down. And if we compare this method to vanilla templated text, which is not an entirely fair comparison, but if we compare it against vanilla templated text, you see that it almost doesn't recover the key, whereas the neural network, after about 5,000 traces there, actually recovers the key. The reason I'm saying it's not entirely fair is we just run templated text also on the raw data. Normally you would also do that alignment and the filtering yourself and get to that point, but we kind of want to take the human out of the equation here, so you can compare them side to side. So okay, we've done AES, let's do ECC. Completely different algorithm, of course. In this case, we're looking at Curve 25519, and it's implemented using a Montgomery ladder and scalar blinding. For those of you who don't know what scalar blinding is, I'm not going to explain it right now, but you can't use the nice trick of accumulating more and more traces. You actually take one trace, and you can only be off by a couple of bits in your key recovery. So here you need to be very precise at the modeling and then extracting the right key bits. This is obviously quite a messy signal. And let's see how it did. So in fairness, there was one pre-processing step that we still did, which is actually cutting up the trace. So we take this long trace, which is one ECC computation, and we cut it up into the individual loops of the Montgomery ladder. But after that, that's what we fed into the deep learning algorithm. And we used our normal attacks, so unsupervised and supervised horizontal attacks, which gives us about a 60% success rate, which is actually not that great. If you do a random coin flip, you get to 50% in this case. Deep learning, after fiddling with the network, we actually got to 90%. And after we did data augmentation, we got to 99.4% success rate. And those for you who are fast at math, the 0.6% of a 256-bit key is just a few bits. It's like 1 or 2 bits on average. So those you just brute force, and then the full exponent comes out, and then you're done. Again, we use data augmentation here, so to artificially create misalignment in order to train a network to recover for that. So this was quite a cool result, because we've now done on AES, we've done on ECC, and it's also we have to be more accurate here, so that's also cool. In this case, the network was bigger than we've used before. So we have 3 convolutional layers. We actually have 4 dense layers of 100 neurons. But really, if you look at classifying cat pictures versus this is not a very big network. So I can still do this on my poor CPU. This is where it gets interesting, at least in my opinion. Here we take an example of a so-called masked implementation of AES. It's actually part of a competition called the DPA contest. And here they invite, well, basically anybody who can download a trace set to try to break them. So it attracts a lot of scholars and academics and hobbyists to try to get the key out in the fewest number of traces. But really our goal here is not to extract the key in the fewest number of traces. We're trying to just replace the human. The countermeasure that they use here is something called a rotating S-box masking. I won't go into all the details, but I want to give you a bit of an idea what masking means. The idea is that you break, or you try to break the relation between that value of S0 that's being processed and the power consumption. And you do this by, before you do an AES, or yeah, in this case an AES, you flip a random mask, you modify your S-boxes a little bit, and you XOR that mask onto your data. It then goes through the key addition, the mask just survives, it goes through the S-box, and out comes again another masked value. And before you get to the end of the algorithm, you basically unmask it again, and your regular AES result comes out. So, because this mask is at least supposed to be random every time you invoke, as an attacker you cannot predict anymore what S0 is, because it's just masked by this random thing that you will never see. Now there's attacks on this, which are called second order attacks, and they basically rely on the idea that if you have 2 points in time that are masked, and you cannot really predict what the masked value is going to be, but you can predict the unmasked values. Now what you can actually do, if that mask is being used for both values, so you take X XOR M, and you XOR that with Y XOR M, and it basically is the same as X XOR Y. So this is a value that you can calculate without knowing the mask, and you can combine the two power measurements at which this masked value is present by multiplying. And that actually will give you a correlation between X XOR Y and these samples. The problem with this is that if I don't know where I and J are, where those 2 points in the trace are, I basically need to brute force through that trace, which is it's actually squared complexity. I'll fix that later. So it's n squared over 2 or so within the number of samples in your trace. So it's quite costly. It's also costly to implement, by the way, to do this stuff. It slows things down if you're doing in hardware, your area blows up, etc., etc. So you don't see this a lot. We had actually one tricky thing to overcome when we were doing this analysis, and that is that normally you want your validation key to be different from your training key. Because it's kind of unfair if you're training on one key and then you're validating the same key, you might be overfitting without knowing it. So we actually developed a simple test to figure out whether you're doing the right training or not, which is to train on completely the wrong key. And if you then see that your network is still training, then it's actually not learning anything. It's just learning random data. So that's one good way to find out whether your network is properly training in this case or not. The other thing, and we'll be publishing more results about this in a paper soon to be released, is to kind of reverse the network. So once you've trained on a network, you can actually query it to see which input neurons were firing really strongly for a particular output. And that gives you an idea of what in the input is actually causing this leakage. So if you look on the left-hand side here, you see a picture where there's a couple of really distinct spikes. And that's sort of what you want to see. And on the right-hand side, you see kind of spikes all over the place. And that's usually not how leakage works. So then you also know that you're doing something wrong. So going into the results, and actually I can show this one as well. So let's open the DPA contest. I'll run our deep learning. This time I will use the correct network. So I'm using a convolutional neural network, only one convolutional layer and 3 dense layers. And I'm going to let my poor CPU run for a little while. But if my sacrifices to the demo gods have paid off, we'll see is that we will recover the key in extremely few traces. Actually, in this case, 8 traces was sufficient to get the full key out. And this is mind-blowing for reasons other than you're thinking right now, I think. There's 2 reasons why this is mind-blowing. The first thing is this actually shouldn't work. We have a masking scheme where we have to predict X, XOR Y, right? We didn't feed it X, XOR Y, we just fed it X. So we were just doing a first order attack. We were just being stupid, really, if you think about it. We're still kind of hypothesizing why it did work. But what seems to be happening also, if you look at the other contestants in the DPA contest, is that there is actually some hidden first order leakage in these traces. You don't find them by just running normal template attacks. We can, I think the numbers were about 45,000 traces for training, and then about 5,000 traces for the test set. Then with template attacks, we could get the key down to rank 5 or so. 5,000 versus 8. So there is some first order leakage in there, but templates can't find it. This did, which was really cool. The second thing that I think is really cool is that our really stupid network, in which the human interaction was just fiddling until the accuracy and the recall looked good, is actually up there with dozens of side channel, world-class teams. So just by being stupid and putting in this deep learning network, we were ranking there as well. So yeah, I find those really, really fascinating. That wasn't even what we're aiming for, right? We're trying to get people a little bit out of the loop of the signal processing, but this thing actually found an attack route. So getting more to the last part of what just happened here? Getting more into the leakage modeling part of everything. So this was really cool. So just to wrap up, now is a good time to start thinking about those excellent questions, by the way. If you want to learn more, so there's a few resources that I can recommend. So first of all, there's a deep learning book, which you can read online. There's also a really excellent MIT course that kind of teaches you all the basics. These are videos that you can watch online, intro to deeplearning.com. There's a book on DPA called Power Analysis Attacks by Stefan Mangard, which is kind of historically the book to go for. And then Colin and I are still working on it. We're doing our best, but it will be there at some point. We're writing a book on these kind of topics as well, with a more practical side to it. So really, if you're going to walk away with 3 things, deep learning really takes side channel analysis and it performs both the art part and the science part of it, which was more than we were hoping for. And importantly, it also scales, right? If I can do it on my laptop here, then GPU clusters can do much more. The bar is definitely not at 0 yet. This is not fully automated. You still need to fiddle with the network, but you don't quite need the same kind of expertise for that. A couple of guidelines and fiddling and getting a sense for this network might work is already getting you up there with world-class teams. And really, this kind of automation is needed to put a dent in all the embedded insecurity that we're seeing. So I'm really excited about where this is heading. So I'll leave some references for the slides later. So I'll be posting these slides online as well. If you follow me on Twitter, I'll post a link there probably within a week. If you have any questions, you can either email me or we can take a couple of questions right now live. Once we're out of time, we'll head out to the wrap room, which is where? Just down the hall. Just down the hall. So, time for those excellent questions. Thank you.
Thanks for the excellent talk, Jasper.
Thank you.
I have a question about this threshold of 1/9
Yeah.
that you're saying if your testing accuracy isn't any better than this, then your machine learning hasn't learned anything.
Yeah.
But you can do a lot better than 1/9 because Hamming weights aren't randomly spread over all 9 classes. So I think you can do better just by always predicting Hamming weight of 4. So that threshold of 1/9 should be a lot higher. Can you comment on that?
It's a good question. So the question is, shouldn't you be able to do better than 1/9 because Hamming weights aren't uniformly distributed? I'm not sure if I can give you exactly the right answer right now, but intuitively I'm thinking that the network actually doesn't know that this distribution exists. So I think it assumes thereby implicitly a uniform distribution. You might be able to tweak the network not to have this, and maybe the training data will do this for you, but it's too complex of a question for me to give you a closed answer right now.
Thank you.
Yep.
So, just curious, did this save you time? I mean, in between a human having to do all this or the training of the AI, everything else, which one was quicker?
Yeah, good question. So the question is does this save you time? I'm going to ask you a question, so maybe stay close to the mic. Are you talking about wall clock time, CPU time, human time?
All of it, actually.
All of it. Okay, good question in that case. So definitely this is more CPU intensive. That's the easy one to answer. So this is like when we're doing traditional side channel analysis, yeah, you're doing a bit of filtering, you're doing a bit of correlation attacks, but this is doable. Training a deep learning network will take longer. Like the trace sets that I just showed you can take up to a few hours to fully go through all the through all the keys. And I'm just reminded now that I had one session running. And for those of you who stuck around, 6C, 6C. So it found the key. But thank you. Thanks to my colleagues. Human time, in our experience, there's a bit of a learning curve to figure out like how to tune the networks. But after that, it's definitely not as long as the filtering. And that has to do with filtering, or sorry, the traditional approach. You have multiple of these loops where you kind of wait for your filtering to end and you see how it is. Then you do your misalignment, you have to go back. Here there's fewer of these interrelated loops. So once you've kind of twiddled your network, then it turns into CPU time. So wall clock time, I find that one hard to answer. I would guess that it will save you a bit of time, wall clock, but for a single execution, but you can parallelize this much better, right? You can run many more deep learning algorithms in parallel than humans fiddling knobs. I think we're almost out of time, so if there's more questions, I'll be heading out to the break room. Thank you very much for listening.